plus 5ab to the fourth, and plus 1b to the fifth. Okay. And on this is going to go. Okay. So this could go till the end of time, literally. But notice the higher the power assigned to the binomial a plus b, the more difficult it is and more time consuming it is to expand it out. All right. Now I want to draw your attention to several patterns that are inherent in this these expansions, these binomial expansions. Notice the first product, a plus b to the 0th power, yields one term. Okay. A plus b to the first power, we have two terms. A plus b to the second power, we count three terms. A plus b to the third power, we have four terms. There's five terms in a plus b to the fifth power. And there's 1, 2, 3, 4, 5, 6 terms in a plus b to the, I'm sorry, a plus b to the fourth power has five terms. A plus b to the fifth power has six terms. So how does the number of terms in these expansions relate to the exponent or the power the binomial is raised to? How does 1 to relate to 0, 2 to 1, 3 to 2, 4 to 3, 5 to 4, 6 to 5? What's the relationship? Anybody?
It's just the exponent plus 1.
So the number of terms in our binomial expansion is always one more than the power the binomial is raised to. Okay, notice that. Interesting observation there. That'll become important later on. All right, notice another thing here, that all of these binomial expansions, the coefficients start with 1, all start with 1, and they all end with a coefficient of 1. Notice that. Interesting thing there. Notice with all these binomial expansions, the first term of the binomial starts out always at the power that the binomial is being raised to. So like a plus b to the first power, you have a to the first power. A plus b to the second power, you have a squared. A plus b cubed, you have a cubed. A plus b to the fourth, a to the fourth. A plus b to the fifth, a to the fifth. Let's look at a plus b to the fifth power. Another interesting thing occurs here. Notice that the degree on the first term of the binomial, again, starts out at the power the binomial is being raised to, but the degree on the first term decreases as we progress two terms to the right. So a starts at the fifth degree, then it decreases to the fourth degree, third degree, second degree, first degree, and technically a is to the 0th degree here. Okay, now a to the 0th power is really 1. That's why you don't see us listing a to the 0th power. It's understood it's though a to the 0th power. Notice the power on the second term of the binomial starts at always at the 0th power. So this would be b to the 0 power times b to the 0 power, which is times 1. And then b's power increments by 1 as we go to the right. B increments to 1, then increments to, wait a minute here. This should be 2. Then it increments to 2, and then it increments to 3, and then 4, and then 5. All right. And notice that's also true for any expansion here. A plus b to the fourth, a starts out at the 4th power, and then its power decreases by 1 as we move to the right. So 4, 3, 2, 1, and then technically a to the 0th power. B starts out at the 0th power, and then increments by 1. B to the 0th power, b to the first power, second power, third power, fourth power. Okay, so notice the last term of these expansions, okay, always end with the last term of the binomial being raised to the power the binomial is being raised to. So b to the first power, b to the second power, b cubed, b to the fourth, b to the fifth. Another observation is notice the sum of the exponents on any term always add up to the power the binomial is being raised to. 1, first power. 1, first power. 2, second power. 1 plus 1 power, second power. 2, second power. 3, third power. 2 plus 1, third power. 1 plus 2, third power. Third power. Fourth power, 3 plus 1, fourth power, 2 plus 2, fourth power, 1 plus 3, fourth power, fourth power. Fifth power, 4 plus 1, fifth power, 3 plus 2, fifth power, 2 plus 3, fifth power, 1 plus 4, fifth power, fifth power. So there's a lot of patterns evident in these expansions here. And these patterns here that we're looking at, ladies and gentlemen, is going to make our life a lot easier as we become more sophisticated in understanding how to develop these expansions instead of multiplying them out with brute force, which takes a tremendous amount of time, especially when the exponent gets large. All right, now there was a mathematician. His name was Blaise Pascal. He hailed back in the 1600s, and this mathematician came up with a wonderful construction called Pascal's triangle. And this triangle is extremely symmetric and it's very easy to construct. It starts at 1, and then we'll have a 1 and a 1, and we'll have a 1. Now the sum of these two numbers here, 1 plus 1 is 2, and then we have a 1, 1. 1 plus 2 is 3, 2 plus 1 is 3, and we have a 1, 1, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and then we have a 1, and 1, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, 4 plus 1 is 5. All right, and on this will go. Do this another row here. 1 plus 5 is 6, 5 plus 10 is 15, 10 plus 10 is 20, 10 plus 5 is 15, 5 plus 1 is 6, and then 1. Notice that the first entry in any row of Pascal's triangle always starts with a 1 and always ends with a 1. Okay, and so this is called Pascal's triangle. And what does it have to do with these binomial expansions? Well, ladies and gentlemen, let's take a look again at these binomial expansions. We have 1, 1, 1, 1, 1, 1, 1, 2, 1, 1, 2, 1, 1, 2, 1. Then we have 1, 3, 3, 1, 1, 3, 3, 1, 1, 1, 4, 6, 4, 1, 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1, 1, 5, 10, 10, 5, 1. So you can see there is an innate relationship between these coefficients of the binomial expansion terms and Pascal's triangle. In fact, this row of Pascal's triangle gives you the leading coefficient of raising a binomial to the 0th power, which is always going to be 1. This row will provide the coefficients of raising a binomial to the 1st power. This row will give you the coefficients of squaring a binomial. This row provides the coefficients of cubing a binomial. This row provides the coefficients of raising a binomial to 4th power, coefficients of raising a binomial to the 5th power, coefficients of raising the binomial to the 6th power. All right, so that's called Pascal's triangle there, and on this goes on down the line. All right, so you can see it's pretty easy to build Pascal's triangle, albeit it does take some time, especially if you go down towards the very large powers on the binomial here. Okay, and so, ladies and gentlemen, what I would like you to try to do in observance of everything I've shown you so far with all the patterns that, you know, of all the patterns that we've seen so far, okay, with all these expansions and Pascal's triangle, I want you now to try a classwork problem. I would like you to, we'll call this classwork number 1. I want you to take a plus b and I want you to raise it to the 7th power. Okay. Now, the intention here is to make use of Pascal's triangle that affords us the coefficients. All right, and to basically play off of the pattern that I've been speaking of here as we move from term to term, left to right. This is not intended to, you know, have you multiply a plus b by itself 7 times, because that's not only going to take a ton of time, the probability of getting this thing correct is almost non-existent. Okay, so I'm going to have you, based on what we've seen so far with all these patterns, I want you to raise a plus b to the 7th power. So here's the first hint. Here's the step you got to do. First of all, you have to complete this row down here, the 8th row, excuse me. Yes, the 8th row of Pascal's triangle. Based on how I showed you how to generate these numbers, you should be able to generate the 8th row of Pascal's triangle. This row is going to provide you with the coefficients of this expansion. Okay. All right. So see if you can do that. A little bit of a challenge problem. Go ahead and try that out. Classwork 1. So we have 3 factorial over 2 factorial times n is 3, r is 2. So 3 factorial over 2 factorial times 3 minus 2 factorial. And this is going to be 3 times 2 times 1. 2 factorial is just 2 times 1 or 2. 3 minus 2 is 1, and 1 factorial is 1. So this reduces also down to 3. And one more, 3 in combination with 3, or 3 choose 3. N is 3, r is 3. So we'll have 3 factorial over 3 factorial times 3 minus 3 factorial. 3 minus 3 factorial. Well, guess what? The 3 factorials reduce out to 1, and this is 0 factorial, and 1 over 0 factorial is 1 over 1, which is just 1. All right. Ladies and gentlemen, you recognize these numbers here, 1, 3, 3, 1. What row do those come from in Pascal's triangle? 1, 3, 3, 1. You can see them right here. 1, 3, 3, 1. Everybody see that there? 1, 3, 3, 1. All right. So, as it turns out, these combinations actually are used to generate entries of any particular row of Pascal's triangle. Okay. Now, we also have at our disposal on our TI-84 calculator the combination function. And so we don't have to go through all this factorial business here. I would like us to all try this on our calculator. We're going to try to evaluate 3 choose 2, or 3 in combination with 2. Sometimes it's written this way on our calculator. So I'm going to show you now on the calculator how to do that. So you can fire up your machine. Okay. And what we're going to do is, with our screen cleared, first we're going to have to enter in 3, because I want 3 choose 2, or 3 in combination with 2. So we're going to hit 3 first. We're going to hit our math button, math. And then we're going to go over to the probability menu, PROB, and then we go down and grab the combination function, NCR. That's your combination function. So 3, enter, in combination with 2. Hit enter, boom, you get 3. So 3 in combination with 2 is 3. So that way this bypasses us having to go through the factorial function. Everybody understand how to use the combination function on the calculator? All right, try another one here. Try this one. 5 in combination with 3. So 5, math, probability menu, combination function. 5 in combination with 3, enter, answer is 10. We all understand how to use that combination function. Any questions about this? All right. That's all there is to the combination function there. Well, ladies and gentlemen, as it turns out, these combinations can be used to generate Pascal's triangle and any row of that triangle. All right, so here's how you generate the entries of Pascal's triangle. This, the 1 at the top is generated by 0 in combination with 0. The 1 and 1 are generated by 1 in combination with 0, 1 in combination with 1. This will generate the entries of 1, 2, 1. 2 in combination with 0 is 1. 2 in combination with 1 is 2. 2 in combination with 2 is 1. This row will generate the entries of 1, 3, 3, 1. This row generates the entries of right here of 1, 4, 6, 4, 1. These combinations will generate the entries of 1, 5, 10, 10, 5, and 1. All right, so that's how you can generate the entries of this particular Pascal's triangle, is by using the combination. All right, and notice with our combination, how does n relate to the row of Pascal's triangle? Notice this is this is row 1. Row 1. This is row 2. Row 3. Row 4. How does the row of Pascal's triangle relate to the power on the binomial? The row of Pascal's triangle is always what? 1 more than the power of the binomial is being raised to. Okay. So for row 1, notice n will be 0. For row 2, n will be 1 for all your combinations. For row 3, n is 2 for all your combinations. For row 4, n is 3. And for row 5 rather, n is 4. For row 6, n is 5 for all your combinations. Notice r is always equal to the power the binomial is being raised to, or it starts out at 0. R starts out at 0 and then terminates at the power the binomial has been raised to. So 0th power starts at 0, ends with 0. First power, r starts at 0, ends at 1. The second power, r starts at 0, increments to 1, and terminates at 2, the power the binomial is being raised to. Raising the binomial to third power, r starts at 1, increments to 1, 2, and then terminates at 3, the power the binomial is being raised to. Raising the binomial to the fourth power, r starts at 0, then goes to 1, 2, 3, and terminates at 4. So do we understand the relationship between the rows of Pascal's triangle, the power the binomial is being raised to, and how n and r of the combinations relate to all of that? Okay. Any questions about that? So we can generate all of those entries of the Pascal's triangle by using combinations, which therefore, ladies and gentlemen, now enables us to formally show you what this whole section is really about. Very interesting theorem called the binomial theorem. So the binomial theorem. All right, so we're going to let n be some positive integer, like 1, 2, 3, 4, 5, 6, 7, etc., etc. Then the expression a plus b to the nth power is going to be given by this expansion. The first coefficient of the first term of this expansion is going to have n be equal to the power the binomial is being raised to. R starts out at 0. So n in combination with 0 will generate the first coefficient of this expansion. The first term of the binomial expansion always takes on the power the binomial is being raised to. Plus, now we go to the next term, and the coefficient of the next term will still have n be n, and which is the power the binomial is being raised to, and r increments to 1. And the power on the first term decreases by 1, and the power on the second term increases by 1. The next term's coefficient will be n in combination with 2 times a's power decreased by 1 again, and b's power increased by 1. Okay. Plus the next term's coefficient will be n in combination with 3 times a's power decreased by 1 again, and b's power increased by 1. Plus dot, 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 on and on this is going to go on down the line until you run into the last two terms. Next to the last term, we'll have n in combination with n minus 1 times a to the first power times b to the n minus 1 power, plus the last term's coefficient will be n in combination with n times a to the 0th power, which we don't even list because a to the 0th power is just 1. And so it will be b to what power at the end? It's going to be b to the what? To the nth power. And you are looking, ladies and gentlemen, at the binomial theorem, which is basically formalizing things that I've already been kind of talking about and going over. All right, so we can see the pattern that's being laid out here. Now, when you're raising binomials to small powers, I mean, you don't actually have to compute all these combinations on your calculator. You can just, get the coefficients from Pascal's triangle. I mean, it's not difficult to go down, 3 or 4 rows in Pascal's triangle. It's very easy to construct. If you insist on using your combination function on your calculator to generate these coefficients, be my guest, no problem. All right. Any questions? That's the binomial theorem. All right, let's try this out here. Let's try to expand out 2x plus 3 to the 4th power. Okay. Well, ladies and gentlemen, we're going to follow along what the binomial theorem says here. The expansion of this is going to have our first coefficient be generated by taking the combination of 4 in combination with 0. That will generate the first coefficient of our first term. And the first term is 2x. And 2x, the first term, always starts out at the power the binomial is being raised to. Plus the second term, our second term's coefficient will be 4 in combination with 1 times the first term's power decreased by 1 down to the 3rd power times the second term's power increased by 1. One other thing I just want to point out with the binomial theorem, notice the sum of the exponents is always equal to the power the binomial is being raised to, nth power. N minus 1 plus 1 adds up to nth power. N minus 2 plus 2 adds up to the nth power. N minus 3 plus 3 adds up to the nth power. 1 plus n minus 1 adds up to the nth power. Nth power. Okay. All right, so let's continue on with this expansion here. Plus, the next coefficient would be 4 in combination with 2 times the first term's power decreased down to the second power, and the second term's power increased to the second power. Plus, the coefficient for the next term is 4 in combination with 3. First term's power decreased down to the first power, and the second term's power increased to the third power. Plus, finally, 4 in combination with 4. First term's power is down to the 0th power, which makes it just a factor of 1. And the last term's power increments to the power of the binomial, 3 to the 4th power. Now it's just a matter of cleaning this up here. And 4 in combination with 0. Or, ladies and gentlemen, you could use just what? The 5th row of Pascal's triangle. It's not difficult to build Pascal's triangle down to the 5th row very quickly. And you can just use the coefficients from this 5th row. If you want to use the combination, 4 in combination with 0, 4 in combination with 1, 4 in combination with 2, 4 in combination with 3, 4 in combination with 4, be my guest to crank these out. It's up to you. Okay. So this will be 1. Now 2x to the 4th power, 2 to the 4th power is 16, and then we're going to have x to the 4th. 4 in combination with 1 is going to give us 4. So we'll have 4. Now 2x cubed, 2 cubed is 8. That's times 8x cubed times 3. Plus 4 in combination with 2 is going to generate 6. 2x squared, 2 squared is 4. X squared times 3 squared is 9. Plus 4 in combination with 3 is going to give us 4 times just 2x. And then 3 cubed is 3 times 3 times 3, which is 27. Plus 4 in combination with 4 is 1. And 3 to the 4th power is 3 times 3, which is 9, times 3 is 27, times 3 is 81. This will be just times 81 at the end. All right, cleaning this up further, simplifying, we have 16x to the 4th. This is 4 times 8, which is going to be 32, and 32 times 3 is 96. So we got 96x cubed. 6 times 4 is 24, and 9 times 24 is what? What's 9 times 24?
216.
2 plus 216, x squared. 4 times 2 is 8. 8 times 27. 8 times 27. 2. Is that also 216?
Yes.
That's also 216. I'll be darned. X and plus 81 at the end. That would be 2x plus 3 to the 4th power is expansion. Okay. Now this looks like a lot of work, but I'll tell you one thing, it's nothing compared to if you had to multiply this by itself 4 times, which would take some time. And this would become even, the binomial theorem becomes even more attractive if you were to raise this to like to the 6th power or something, because trying to do that manually would take a tremendous amount of time. It's so much easier just to adhere to the binomial theorem and the patterns that it's laying out here. All right, so let's see what time it is. 3:13. Okay, let's see how much more we got here. Don't want to get behind the 8 ball with the clock. All right. Okay, maybe we could try another one here. Any questions about this expansion here? All right. All right, so let's see. All right, trying to conserve paper a little bit here, ladies and gentlemen, so just disregard all this garbage off here. All right, let's try this one here. Let's try to expand. Now, all right, so we'll try to expand 3x squared minus 5y to the 4th power. All right, using the binomial theorem. So the first coefficient is going to be 4 in combination with 0. Then we're going to have our first term, 3x squared, being raised to the power of the binomial. Plus, next coefficient is 4 in combination with 1. First term's power decreases to the 3rd power. The second term's power increases to the 1st power, negative 5y to the 1st. Yes, the last term of this binomial is negative 5y. Okay. Plus, then our next coefficient is 4 in combination with 2 times 3x squared down to the 2nd power. The second term is negative 5y to the 2nd power. Just remember, the sum of these exponents have to add up to the power of the binomial. Okay, the power of the binomial. Then we have 4 in combination with 3, 3x squared to the 1st power, negative 5y to the 3rd power. 1 plus 3 gives us the power of the binomial. Looks good. And my last term here is going to be 4 in combination with 4 times 3x squared, technically to the 0th power, and negative 5y to the 4th power. Okay. We really want to clean this up, though. And notice our coefficients come from the 5th row of Pascal's triangle, or you can use your combination function on your calculator to generate all of these. But it's up to you. I don't really care how you generate them. We just got to get them generated somehow. So first coefficient is going to be 1. We're going to have 3x squared to the 4th. Plus this coefficient is going to be 4. Now we're going to have 3x squared cubed times negative 5y. And 4 in combination with 2 would be a coefficient of 6. This here. And then this next coefficient would be a 4. Okay, so plus 4 times 3x squared to the 1st power times negative 5y cubed. And the last coefficient here at the end is going to be 1. 1 times 1. And so we're just going to have negative 5y to the 4th power. Okay. All right, so let's get more serious now and simplifying this. 3 to the 4th power is going to be 81. So we have 81x to the 8th power, x squared to the 4th. We multiply these exponents, so it's x to the 8th. All right, and here we're going to have plus 4 times 3 cubed. 3 times 3 times 3 is 27, so that's times 27 times a negative 5. And then we're going to have x to the 6th power and y. This is going to be plus 6 times, this is 3 squared, which is 9 times negative 5 squared is negative 5 times negative 5, which is 25. And then we have x to the 4th power. And then y squared plus, this is going to be 4 times 3. Negative 5 cubed is negative 5 times negative 5 times negative 5, which is negative 125. We're going to have x squared, y cubed. And then negative 5 to the 4th power, negative 5 times negative 5 times negative 5 times negative 5 is going to be 25 times 25, which is 625. So 625y to the 4th at the end. All right, further simplification here. We got 81x to the 8th. Anybody, let's see here. We got negative 20 times 27. Negative 20 times 27 is going to be negative 5, 4. Wait a minute here. Negative 540, is that correct? 4 times 27 times negative 5. All this right here.
Negative 540, yeah.
Minus, okay, 540 x to the 6th y. Help me out here. 6 times 9 is 54 times 25. What does this all net us?
1350.
0. And x to the 4th y squared. And then we got 4 times 3 is 12 times negative 125. We're back to a negative term. And that would be negative, whatever this evaluates to on your calculator here. And what does that give you?
1500.
1500 x squared y cubed plus 625 y to the 4th. And we're done with that expansion. Make sense? Now we're expanding these out here. Obviously, your calculator is going to help you, deal with the arithmetic. Right? Okay. So I think we understand how to expand these things out. Now, the next thing here, suppose I did not want the complete expansion of a binomial. What if I was just interested in like a particular term of a binomial expansion? Well, we can develop a formula to help us with that. So we're going to learn how to find a specific term of a binomial expansion. Okay. All right. All right, let's entertain this here. N in combination with 0 times a to the nth power b to the 0th power plus n in combination with 1 a to the n minus 1 power times b to the 1st power plus n in combination with 2 times a to the n minus 2 power b squared plus n in combination with 3 times a to the n minus 3 power times b cubed. And, on and on this would go forever, okay? All right, this is term number 1. This is the second term, third term, and the 4th term. Now, some observations here. Notice, and what we did here, or what we accomplished here, is we're expanding out a binomial here. All right. Now I want to draw your attention to this. How does the term number relate to the exponent on B? 1, 0, 2, 1, 3, 2, 4, 3. What's the relationship between the power on B and the term number?
Power +1 or term -1.
Yeah, so notice the power on B lags 1 behind the term. 1 behind the term. Everybody see that there? 1 behind the term. So this is the first term, power on B is 0. Second term, power on B is 1. Third term, power on B is 2. Fourth term, power on B is 3. All right, that's one pattern we need to observe. The next pattern we need to understand is how does the bottom number of our combinations relate to the power on B? You can see that the bottom number of our combination is equal to the exponent on B. Everybody see that there? All right, so with that, ladies and gentlemen, we can now develop an interesting and very powerful little formula here to find the kth term of a binomial expansion. To find the kth term of a binomial expansion, we're going to let n and k be positive integers with k being less than or equal to n plus 1. Then later on, we say that the kth term of a plus b raised to the nth power, the kth term is going to be the power of the binomial is being raised to, and in combination with the bottom number, which lags 1 behind the term number. And since this is the kth term, the bottom number would be k minus 1. And in combination with k minus 1 would be the coefficient of the kth term. And the power on B, notice, is equal to the bottom number of the combination. Or that's to say the power on B lags 1 behind the term. All right, since this is the kth term, the power on B would have to be k minus 1. What's going to be the power on A? Well, remember, the power on A, which we don't know at this point in time, and we'll call it x, must add to the power on B to give us the power the binomial is being raised to. So x plus k minus 1 has got to be equal to the nth power, because that's the power the binomial is being raised to. Now we can solve for x here. To solve for x, we subtract k from both sides and add 1 to both sides. And therefore, we get the power on A has got to be equal to n minus k plus 1. Or your author, tidies this up and says it's the same thing as n minus quantity k minus 1. That has to be the power on the first term of the binomial for the kth term. N minus k minus 1. Laid out a pretty powerful little formula here. This formula here will enable us to crank out the kth term of a binomial expansion, where we don't actually have to go through and list all of the terms just to get to that particular term of interest. So this expedites things in us, cutting through the chase and just listing a particular term we might be interested in for a binomial expansion. So this is a very important formula that you might want to have handy before you dive into any homework on ALEKS or any assessment on ALEKS. Make sure you have that close by, or at least in your memory banks, okay? All right, so let's see if we can have some fun with this particular formula and see what kind of bills it can pay for us on assessment day. Or any questions so far here about this? All right, how I derived that term there. Okay. Okay, let's see what we can do with it. Well, here's a typical problem you'll run into on ALEKS or any future assessment. Suppose I want to find the 8th term. The 8th term of this binomial expansion, 2x plus y to the 4th power raised to the 10th power. So suppose I want to determine what the 8th term of this binomial expansion is. Now, ladies and gentlemen, without using this formula, this problem is not going to be possible in human terms because you would have to multiply this binomial by itself 10 times. And good luck with that one there. That's just not going to be feasible. So we really have to tap into this formula here. And the formula we developed is the formula enabling us to find the kth term of a binomial expansion in general that looks like this. And that formula is n in combination with k minus 1 times a raised to the n, subtract quantity k minus 1 power, times b raised to the k minus 1 power. That's the formula we're going to tap into to help to answer this question here. Got a question for you. What would my k be for this problem? What term am I interested in finding? I want to find the what? The 8th term. So my k is going to be 8. What's n? What is n for the purpose of this formula here? What's my n? N is the power the binomial is being raised to. So n is 10. What's my first term? Generically represented by a. What's the first term of this binomial? It's 2x. What's the last term of this binomial? Represented generically as b. Last term is y to the 4th. All we have to do, ladies and gentlemen, now is just drop things into the formula that we know up here. So here we go. So the 8th term of this binomial expansion is going to be n in combination with k minus 1. That's to say it's going to be 10 in combination with 8 minus 1, or 10 in combination with 7. That will yield the coefficient. And this prevents you from having to go all the way down to the what? The 11th row of Pascal's triangle. Do you agree? To get this coefficient, just use the formula. Use the combination function on your calculator. Now, my first term a is 2x. So 2x is going to be raised to the n minus k minus 1 power. That's to say 2x is going to be raised to n, which is the 10th power, minus k is 8. That's the power that this first term is going to be raised to, times the second term, which is y to the 4th. And that's going to be raised to the k minus 1 power, k being 8. So this will be raised to the 8 minus 1 power. And that's it. All right, I want you to get on your calculator and I want you to dial up what's 10 in combination with 7. Go ahead and get it. Of course, that's represented notationally also by writing it this way. 10 in combination with 7. Go see if you can do that on your calculator. Make sure you're able to generate this on your machine, ladies and gentlemen. Need to know this coefficient. What would that give us? 10 in combination with 7. Oh.
120.
120, correct? 120? Are we all getting 120? Just make sure you can do that on your calculator, okay? Because, you know, we're going to need to know how to do this. And another way to get this 120 is to take Pascal's triangle all the way down to the 11th row. But that is so not the way to be going about things, all right? That's going to take too much time. Just use your combination formula on your calculator here. All right, so this is 120. Now this is going to be 2x raised to what power? What is all this simplified to? We got 10 minus 7 is what? 3? That'll be the 3rd power. And this is going to be y to the 4th power raised to the what? 7th power. We're getting closer to our 8th term here. Our 8th term is 120 times 2 to the 3rd power times x cubed. And this is going to be y to the 4 power raised to the 7th power, which is y to the 4 times 7, or y to the 28th power. This is going to be 8. What's 8 times 120? I believe that's 960. X cubed, y to the 28th. Ladies and gentlemen, we are done. This would be the 8th term of this binomial expansion. That would be the 8th term. Any questions how we generate the 8th term of that binomial expansion using our formula here? Right up here, this formula. When you're trying to find a term, you need to determine all this information. You got to know what k is, what term it is, what the power on the binomial is, what your first term is, last term is of your binomial. And then you're off and running, okay? Any questions how we found that? The 8th term. All right, that's one very typical problem you could run into, all right, in the future. Okay, here's another typical problem. This next one says, find the term containing a to the 9th power. In the expansion, the binomial expansion, which is going to be a cubed plus 4b raised to the 6th power. They want us to find or determine the term that would contain a to the 9th power in it for this binomial expansion. How are we going to do that? Well, to the rescue is our formula, n in combination with k minus 1 times a raised to the n minus quantity k minus 1 power times b raised to the k minus 1 power. This will give us, of course, the kth term of any binomial expansion, that formula. All right. How can we make this formula work to help us with our situation? Well, ladies and gentlemen, all I know is that I'm going to be interested in, what term am I going to be interested in? The first or the second term, if I'm interested in determining which term has a to the 9th in it. First or second term of this expansion, which one am I going to be interested in? What do you think? Am I going to be interested in 4b, the last term, raised to a power? No, I'm not concerned what b is. We don't care what b is. We just care what, the term that has a to the 9th in it. So it's going to be the first term that we're concerned with. All right, so in general, to find the kth term for our first term of this binomial expansion, it's going to be a raised to the n minus k minus 1 power. But, ladies and gentlemen, we need to insist that this equals our term of a to the 9th power. So we must force this to be equal to a to the 9th power. And now we have to fit in what we know here. What's n? What is n equal to? What would n be equal to here? N. What is n? Well, n is going to be equal to the power the binomial is being raised to, which is to say n is 6. So therefore our n is 6 here. So we have a raised to the 6 minus, do we know what k is? Do we know what term contains a to the 9th? We don't know what term that is. So k remains as k. We're going to have to solve this equation for k. And since we have the equivalence between like bases here, we can equate the exponents. There's actually a theorem in mathematics that says that if a to the mth power equals a to the nth power, then the exponents have got to be equivalent to each other. All right. This theorem, unlike most theorems, actually seems very intuitive. It makes sense. It's pretty logical, pretty obvious. So therefore, I'm going to equate the exponents. So 6 minus quantity k minus 1 has got to be equal to 9. Now we just solve for k. I can distribute the negative sign in here, and we have this here. Solving this first degree equation for k, 6 plus 1 is 7, so we got 7 minus k equals 9. Solving for k, subtract 7 from both sides, implies that negative k is going to be equal to 2. Therefore, k is going to be equal to negative 2. Wait a minute. I did not do that correctly, ladies and gentlemen, because I don't have my first term correct here. What is the first term of my binomial? It's not a, it's what? My first term of my binomial is a cubed. So the first term a is really a cubed here. All right, but I do have the right idea here. It's just that I need to replace a, my first term, with the first term of the binomial, which is a cubed. So I have to replace this a with a cubed here. So this is an error. So I'm going to pick up right here. off of here. This still has to be true. All right, we still have to force this to be equal to a to the 9th. So I'll replace this a with what the first term of my binomial is, which is a cubed. And so therefore I put a cubed in here. So I'll have a cubed raised to the n minus k minus 1 power. And this better walk out with the value of being a to the 9th. So when I raise a power to a power, I multiply the exponent. So this is saying a raised to the 3 times quantity n minus k minus 1 power. And that's equal to a to the 9th. So now I'm going to literally equate the exponents. So I'm literally going to set 3 times n minus k minus 1 equal to 9. And now we got to solve this equation for k. I'm going to divide both sides by 3 first to knock this 3 out here. Therefore, I'll have n minus quantity k minus 1.
Should you replace n with 6?
And n should be replaced with 6 also. That is correct, because we do have 6. We're raising our binomial to 6 power here. So whether you do it at the beginning or later is up to you, but eventually, yeah, it has to go in there. So we got 6 minus quantity k minus 1 equals 3. We can now solve for k. Distributing the negative sign in here, we got 6 minus k plus 1 is equal to 3. 7 minus k equals 3. Solving for k, subtract 7 from both sides, we get negative k is equal to negative 4, and k walks out of this with a value of 4. So you know what, as it turns out, ladies and gentlemen, the term that contains a to the 9th in this binomial expansion is going to be the 4th term. It's the 4th term. So it's the 4th term that has a to the 9th in it. And so now that we know it's the 4th term, we can actually find the term by tapping in again to our formula. So we're going to really try to find the 4th term, because that's what k is equal to. So our k is equal to 4, n is equal to 6. Our first term is a cubed, and our second term of the binomial is 4b. Now we just drop things into our kth formula, which is n in combination with k minus 1 times a raised to the n minus k minus 1 power times our second term b raised to the k minus 1 power. All right. So we're going to have n in combination with k minus 1. So that's going to be 6 in combination with 4 minus 1, or 6 in combination with 3. What is this going to be equal to? Why do I not have to go through this song and dance again here? Because what has that got to be equal to? It's got to be equal to what? a to the 9th. Do you agree? Doesn't have to be equal to a to the 9th. That's why we went through everything we did here. Okay? To find that that's the 4th term. So this is a to the 9th. We know that. Now the second term of our binomial is 4b though. So you have to put 4b in here. And that's going to be raised to the k minus 1 power, k being 4. So k minus 1, or 4 minus 1 is 3. What's 6 in combination with 3? Anybody? Dial that up on your calculator. What does that give you? 6 in combination with 3.
20.
All right, so we got 20 here. So therefore we're going to have 20 times a to the 9th. And then we got 4 cubed, which is 4 times 4, which is 16 times 4 is 64. And we got b cubed. Now 20 times 64 is going to be 128 with a 0 tacked on the end. And there you go, ladies and gentlemen, we are done. This would be the term, the 4th term of that binomial expansion that contains a to the 9th. And we're done. Sorry for this initial little glitch up here, which burned unnecessary time. But do we understand how we found the term that contains a to the 9th? So we found the term that contains a to the 9th for this binomial expansion. And that term is this. This is the term. That's the 4th term. Any questions how we went about that?
Could you go back to the last page,
All right. We're on the last page.
the bottom?
At the very bottom, I'm solving for k. So I must insist that a to the 3rd power raised to this power must be equal to a to the 9th, because that's what we're interested in. And so I equated these exponents. And then I just have to solve this equation for k. I divided both sides by 3 first and knock that 3 out. And I just solve for k. Okay.
You can go.
And I got K is 4. Okay, so that is the fourth term. All right. All right, show you another one here. Trying to show you one of each type. Your author really loves to shift gears and switch things around very quickly in your textbook. I want to make sure that I expose you maybe to one of each type here, albeit we're fighting the clock as always. Find the middle term of this expansion here, K cubed minus 1 to the 10th power. They want us to find the middle term of this binomial expansion. All right, so got a question for you, ladies and gentlemen. We have to go all the way back to when we opened up this session. And I drew your attention to the power on the binomial versus the term. How many terms the expansion has. How does the number of terms the expansion have relate to the power of the binomial? What was that relationship there again? The number of terms of the expansion is always what? One more than the power of the binomial is being raised to. Okay? So therefore, how many terms is this expansion going to have? How many terms? 10, 9, or 11? How many terms is this expansion going to have?
Is it 11?
It will have 11 terms when we get done. Okay, so they want the middle term. Okay, so think about it. If you got 11 terms in your expansion, just think about it. You got 11 terms. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 terms. What's the middle term of 11 terms? What's the middle term?
Is it the sixth one?
That's correct. The sixth term, ladies and gentlemen, the sixth term is the middle term. There's 5 to the left, 5 terms to the right. You agree? We really have to find the sixth term here. That's what they want us to find. They want us to find the middle term of this expansion. That means we need to find, in other words, we got to find the sixth term. That is the middle term. So now we know what K is. K must be 6. And we know N is the power on the binomial, which is 10. And we know the first term of the binomial is K cubed. And the second term of the binomial is -1. Now we're in business. We can just throw things into our Kth term formula. And in combination with K minus 1 times the first term raised to the N minus quantity K minus 1 power times the second term raised to the K minus 1 power. Just fit things in. So N is what? 10. So we have 10 in combination with K minus 1. So 10 in combination with 6 minus 1, or 10 in combination with 5. That'll provide the coefficient that comes from Pascal's triangle, which would be the 11th row of Pascal's triangle. Okay. Then our first term is what? K cubed. We got K cubed raised to the N minus K minus 1 power. N being 10. Minus K, don't confuse this K with this K, different Ks. K is 6, 6 minus 1, they would have to use a K here. Times our second term B, which is -1, raised to the K minus 1 power, raised to the 6 minus 1 power, raised to the 5th power. There you go. This is going to be our middle term. Now we just have to actually evaluate or, simplify this. What is 10 in combination with 5? Did we do that one already? 10 in combination with 5? That seems awfully familiar. Anyways, I don't know.
It's 252.
We did not do that. So this would be 252. Okay, you could get that on your calculator using your combination function. So we got 252 times K raised to the 3rd power raised to the 6 minus 1 is 5. 10 minus 5 is 5. So that's raised to the 5th power. -1 raised to an odd power. Is it going to be -1 or +1? -1 raised to an odd power. This is just going to be, it'll be a -1. So we have 252 times -1 is -252. K raised to the what? 15th power. Ladies and gentlemen, we're done. That would be the middle term of this binomial expansion. And you got to admit, this is so much quicker than if you were to multiply this out by itself 10 times. It's going to be like the Snickers commercial. Gonna be a while. You know what I'm saying? It's going to take you forever to do it that way. Try to use the formulas. Okay. Make sense there? That would be the middle term of that expansion there. All right. Time check. Okay. All right. Okay, so any questions, ladies and gentlemen, on section 8.5? We covered a lot of ground in 8.5. A lot of different interesting things occurred in there. We introduced ourselves to a combination, which is a function that's also used in counting, of which we'll see in the next section. It's used to help us compute probabilities and a course in probability. We also, were introduced to a very, very wonderful triangle called Pascal's triangle in honor of Blaise Pascal, who, came into this triangle back in the 1600s. You can look at Blaise Pascal's biography if you want. And we also looked at the binomial theorem. And also we developed a very powerful formula called the kth term formula that enables us to crank out the kth term of any binomial expansion. Okay. All right, so we're going to put that section behind us then. And we will now try to do something in 8.6. Okay, so let's put this away. All right, now in section 8.6, the entitlement of the section is called Principles of Counting, ladies and gentlemen. 8.6. Principles of Counting. How hard can counting possibly be? Well, I'll tell you what. You could kill a whole 15-week semester at a university, ladies and gentlemen, going through a course called combinatorics. And in combinatorics, you learn ways of counting. All right. So counting can be more involved than you can possibly fathom. All right. So ways of counting. Let's see if we can go to our textbook. I want to open up by looking at a page here. All righty. So bear with me for a moment. All right, so I'm going to go to the textbook here. And we're going to go to section 8.6. So 8.6. Principles of counting. We're way down here. All right. Let's look at example 1 to begin. Suppose that a frozen custard shop offers 4 flavors of custard, 2 types of syrups, and 2 toppings. If a customer can select 1 item from each group for a sundae, how many different sundaes can be made? Well, we have 4 choices of custard: vanilla, chocolate, mint chip, peanut butter, 2 syrup types, hot fudge versus butterscotch, and toppings, nuts, and granola. All right, ladies and gentlemen, to enumerate all the possible sundaes that can be constructed, we can build a sideways tree. Trees are often used to basically help you enumerate all possibilities of a sample space and probability. So notice we have 4 main branches coming out of the root of our tree, which is right here, and the branch is open to the right. We could choose a vanilla, custard, or a chocolate, or mint chip, or peanut butter. Depending upon what custard we choose, we have 2 choices of toppings, hot fudge, and 2 choices of syrup, hot fudge and butterscotch, and 2 types of toppings, nuts, or granolas here. All right. So you could build one sundae that has vanilla, hot fudge, and nuts, or another sundae that has vanilla, hot fudge, and granola, or another sundae which would be vanilla, butterscotch, and nuts, or vanilla, butterscotch, and granola, or chocolate, hot fudge, and nuts, chocolate, hot fudge, and granola, chocolate, butterscotch, nuts, chocolate, butterscotch, granola, mint chip, hot fudge, nuts, mint chip, hot fudge, granola, mint chip, butterscotch, nuts, mint chip, butterscotch, granola, or peanut butter, hot fudge, nuts, peanut butter, hot fudge, granola, or peanut butter, butterscotch, nuts, peanut butter, butterscotch, granola. That's all the sundaes you can put together. All you gotta do is count how many branches to the very far right, you have in this tree, how many branches you count here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There's 16 possible different Sundays, ladies and gentlemen, that can be constructed from what we have available here. Now, an easier way to determine, 16 possible Sundays is not really to have gone through this tree structure. Although it's cool and everything, it's pretty neat to see how this tree is developed. And actually, trees are aptly suited for searching methods performed by computer systems, ladies and gentlemen. And that's one thing you learn in computer science is how to program trees into computers to perform searching routines or searching algorithms, make use of trees. Binary search trees, they're called. Okay. All right. So let's take a look here. We could have determined there's 16 possible combinations by knowing that there's 4 flavors of custards, 2 syrups, and 2 toppings. So we could have used what's called the fundamental principle of counting. And that fundamental principle of counting, ladies and gentlemen, is right here in the purple box. It says if one event can occur in m different ways and a second event can occur in n different ways, then the number of ways that the 2 events can occur in sequence is m times n. This is called the fundamental principle of counting. Okay. So in other words, the number of Sundays we can put together is the custards can occur 4 ways, syrups can occur 2 ways, toppings can occur 2 ways. 4 times 2 times 2 would give us 16. 16 possible Sundays that could be cranked out. Everybody understand that there? So there's 16 possible Sundays that we can create there, according to the fundamental principle of counting. Okay, any questions about this first example and the fundamental principle of counting here? All right, ladies and gentlemen, we're going to now look at example 2. A computer password must have 3 letters followed by 2 digits. How many passwords can be made if A, there are no restrictions on letters or digits, B, no letter or digit may be used more than once? So in A, we don't really care if we repeat letters or digits. And for that matter, you might want to think about this password as having 5 mailboxes, ladies and gentlemen, three for letters and 2 for digits. So think of 5 mailboxes or 5 slots here. All right. Now, we will assume that passwords consist of only all lowercase letters. Okay. How many lowercase letters from the alphabet can I choose to occupy the first slot? How many letters in the alphabet? A, B, C, D, E, F, G, all the way to Z. How many letters? There's 26. Times, how many letters can drop into the second slot for this password? 26. Times, how many letters can drop into the third slot for this password? 26. Times, now how many numbers can I choose from to occupy the first slot if our password must contain 2 numbers? Now, ladies and gentlemen, our password must contain 2 numerical digits to be more precise. So we can choose from the digits of 0 to 9. Do you agree? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 possible digits that can drop into this 4th slot. Times, there's 10 possible digits that can drop into the last slot. You're looking at the total number of passwords that can be created with 3 letters and 2 digits. Get on your calculator, dial this up. What's 26 times 26 times 26 times 10 times 10? What number do we get? All righty, getting a big old number here. So there's 1,757,600 different passwords you can create. Now, for a human to try to break that code or to come up with that password, it's going to take a while. Computers can do this very quickly, though. Okay, it wouldn't take long for a computer system to go through 1,757,600 passwords. A computer could do that within a fraction of seconds. All right, let's look at part B now. Suppose, ladies and gentlemen, we cannot repeat any digit or any letter in our password. Again, we have 5 mailboxes. How many letters can occupy the first slot for our password? There's 26 lowercase letters from the alphabet. But we keep one of those letters out. So times how many letters do we have remaining that can occupy the second slot? We only have 25 letters. Times, but we keep a letter out for the second slot. That means we only have 24 letters left to occupy the third slot. Times how many digits can go into the first slot? There's 10 digits, but one of the digits we leave out into the slot. That means we only have 9 digits left to choose for the last slot, times 9. This is the number of passwords you can construct if you cannot have any repeated letters or digits in your password. So multiplying all that together, 26 times 25 times 24 times 10 times 9. And that gives us what? All right, I get something smaller, but not really that much smaller. I get 1,404,000 passwords that can be constructed if there are to be no repeated letters or digits. Any questions how we went about that problem there using the fundamental principle of counting? Okay. All right. Well, let's see if we can go look at another one here. Now, what just happened here? What did I just do? I'm not sure what just happened there. Anyways, let's go down here. All right, ladies and gentlemen, let's look at example 3 here. A quiz has 5 true-false questions and 5 multiple choice questions. The multiple choice questions each have 4 possible answers, of which only 1 is correct. If a student forgets to study and must guess on each question, in how many different ways can the student answer the questions on the test? All right, so there's how many true false questions? There's 5 of them. So consider this as being like 5 little mailbox slots. 5 multiple choice questions, and there's also 5 multiple choice questions. So you're gonna have 10 boxes, 10 little slots here. Okay. Now, how many different ways can you answer true false questions?
2.
There's 2 different ways. How many different ways? How many different ways can I answer a true false question, multiple choice question? There's 4 possible responses for each multiple choice question. There's 4 different ways for answering a multiple choice question, correct? All right. So envision it as having like 10 mailboxes here, okay? How many different ways can I answer the first question, which is true or false? There's 2 ways. Times how many ways can I answer the second question, which is true or false? There's 2 possible ways. 2 possible ways for the third question, 2 possible ways for the fourth question, 2 possible ways for the 5th question. That takes care of all the possible ways you can answer the first 5 questions, which are true and false. But you have 5 multiple choice questions, each of which have 4 possible ways of answering. So 4 ways to answer this multiple choice question, this one, this one, this one, and this one. And so, ladies and gentlemen, there's going to be 2 to the 5th times 4 to the 5th number of different ways of answering this quiz. So let's find out how many ways that is. 2 raised to the 5th power times 4 raised to the 5th power. There's going to be 32,768 different ways of answering this quiz. But how many ways will render a 100% score on the quiz? Of all,
One.
there's only one. There's only one combination, ladies and gentlemen, that's going to give you a perfect score on this quiz, 100%. So what's the probability of this student getting a 100% score on this quiz if he or she whimsically guesses at each question? The probability would be 1 divided by 32,768. Let's multiply this by 100%, and let's see what their percent chances of getting 100% on this quiz is. Well, here we go. 1 divided by 32,768 times 100%. Wow. This is only going to be 0.003% chance. That's not even 1% chance. 1% is way up here. This is only 3,000th of 1% chance of getting 100% on the quiz if you purely guess. In other ways, ladies and gentlemen, the bottom line is, the moral of the story is, yes, studying can help. Okay. As opposed to whimsically guessing on a particular assessment. You have a better chance of maybe even winning the lotto. Well, no, you don't. Winning the lotto is even less than this, so much less than this. Okay. All right. But any questions how we did that problem there? All right, time check, 4:03. Okay. Ladies and gentlemen, we're now going to introduce ourselves to something called a combination. Wait a minute, doesn't that sound familiar? Where did we hear that word before? We already heard that word back with the binomial theorem. Combination. A combination is a function that enables us to enumerate possible outcomes or arrangements. Okay, we've already seen the notation. N choose R, or N in combination with R. That's a popular notation. This is equally popular in many textbooks. And we already discovered that it can be computed by using your factorial function. But we don't need to bother with this because we have a function which is the combination function built in to our calculator. Let me show you what this combination is really all about now, as far as applying it to actual worldly situations. Suppose, ladies and gentlemen, we have 4 people. We have Ben, Sue, Jane, and Troy. So suppose that I want to form teams of 2. Question is, how many teams of 2 can I form from these 4 people? Now, with combinations, ladies and gentlemen, order does not matter. Order does not matter. As far as forming these teams of 2 people are concerned, I don't care in what order I select these people. I just have to have a team of 2 people. Okay? So, how many different ways can we form teams of 2 people here? Well, we could have Ben and Sue be on one team. Why would I also not count Sue and Ben? Why don't I count Sue and Ben if I already have Ben and Sue? Why not? Because order what? Does not matter. I don't care in what order I selected the 2 people. All I care about is I have a team of 2 people. We don't count this one. Okay. All right. I could have Ben or Sue. I could have Ben or Jane form a team. I could have Ben or Troy. Or, ladies and gentlemen, I could have Sue or Jane. Or I could have Sue and Troy. And one more, Jane and Troy. There we go. Notice we have what? There's 6 possible different teams. 6 teams of 2 people. 6 teams of 2 people. Now, Order does not matter. So another way I could have determined there's 6 possible combinations. Oh, I gave it away. 6 possible teams of 2 is I could have used my what combination function up here. And so, ladies and gentlemen, to find out how many teams of size 2 I could arrange from 4 people where order does not matter, I could have just said 6 in combination, wrong, 4 people in combination with 2. I could have just used my combination function on my calculator. Go ahead and dial it up, ladies and gentlemen. 4 in combination with 2. Do we get 6? Is that 6?
Yes.
That should be 6. Okay. So there's 6 possible arrangements of teams of size 2 that I can form from 4 people, choosing from 4 people. Any questions about this situation here? Now we can more clearly understand what combinations can be used for. Okay. All right. 6 possible teams here. Okay. Ladies and gentlemen, suppose I have 30 people to choose from. Ooh, that might be nasty. I guess we could try that. Suppose we have 30 people to choose from. How many teams of size 10 can we form where order does not matter? Now, if you think I'm going to go through and enumerate all these teams of size 10 from 30 different people to choose from, stop and think how long that's going to take. That's going to take just a phenomenal amount of time to get done. Humans would not be able to do this, ladies and gentlemen, unless you have a computer mind. But I know I couldn't do this. If you can do this in your mind, you have got to show me that trick. Okay. All right. Now we use our combination function. So we have 30 choose 10. 30 in combination with 10. Get on your calculator. Ooh, big question. Can your calculator even handle something like this? Let's see if your calculator can handle this. These are big numbers and combinations grow quickly. So I don't know. Well, factorials grow quickly, right? Well, it works. Big old number. How do we read this number? There are how many teams of size 10 that can be formed from 30 people if the order in which we select them does not matter? There's 30,045,015 teams. Could you imagine trying to sit here on your piece of paper here, trying to enumerate all of those teams of size 10? Not only would it take a long time, ladies and gentlemen, the probability as human beings of getting that correct is almost, well, how shall I say it? It's pretty much 0% chance. All right. This is a situation where computers come in very handy, okay, in dealing with large numbers involving combinations and or permutations. All right, now I want to paint a picture for you as we roll into 410 here as to, ladies and gentlemen, what a permutation is. Permutation. Unlike combinations, with permutations, order matters. Order now matters. Combinations, order does not matter. Permutations, order matters. Suppose I go back to my example, ladies and gentlemen, of Ben, Sue, Jane, and Troy. Okay, so I go back to my example there. All right, going back to the same people. I want to form a committee or a cabinet of size 2, where one person's going to occupy the office of president. The other person's going to occupy the office of vice president. How many different ways can I form this cabinet from these 4 people? Why does order matter now? Well, order does matter because, ladies and gentlemen, whether you're president or vice president can mean a huge difference in many things. Your income, do you agree? The power that you wield, all right, whatever. Anyways, you agree I could choose Ben to be president, Sue to be vice president, or I could choose Sue to be president and Ben to be vice president. These are different now because order matters. We got to count them. Well, I could choose Ben to be president, Jane to be vice president, Jane to be president, Ben to be vice president. Or I could choose Ben to be president, Troy to be vice president, or Troy to be president, Ben to be vice president. Or I could choose Sue to be president, Jane to be vice president, Jane to be the president, Sue to be the VP. Or I could choose Sue to be the president, Troy to be the VP. Hold on. Or I could choose Troy to be president, Sue to be vice president, or Jane to be president, Troy to be vice president, or Troy to be president, Jane to be vice president. Ladies and gentlemen, there are 12 different cabinets of size 2 that I could arrange from these 4 people where order now matters. How to get 12? We don't use a combination function anymore. We use what's called a permutation function. And ladies and gentlemen, this is the formula for computing n permuted R ways. This is n permuted R ways. P stands for the word permuted or permutation. It's n factorial divided by n minus r factorial. What factor is missing in the denominator of this formula that the combination formula has? Anybody?
R factorial.
R factorial. Because it's missing R factorial, the denominator of a permutation is always going to be smaller than the denominator of a combination, which, ladies and gentlemen, renders the certain fact that a permutation is always going to be greater than a combination. Everybody see that there? It makes sense, because if order matters, you have more different possibilities for, you know, a cabinet or a team of size 2. You're going to have more possible choices. So it makes sense that a permutation is going to yield more choices than or possibilities as opposed to a combination. Now, I want you to get on your calculator. I want you to clear your screen. I want you to type in 4, go to probability or go to math, probability, and grab your NPR function, your permutation function, and then type in 2. You should get 12. Let's see if we can do that quickly. So on our calculator here, it's called the permutation function. So we're going to type in 4 math probability permutation 4 permuted 2 ways. Okay, and we get 12. So there are 12 possible cabinets of size 2. Okay. Any questions? How we use the permutation formula there. So it's NPR, not NCR. All right. Okay. Now, suppose, ladies and gentlemen, we have, let's say, 30 candidates to choose from. And I want to form a cabinet where my cabinet has a president, a vice president, treasurer. Anybody else? What else do we need? President, vice president, treasurer, anything else? Secretary, maybe? I don't know, maybe secretary. How many different cabinets can you arrange from 30 candidates, ladies and gentlemen, if you got to fill the presidency, vice presidency, treasury, and the secretarial position here? It's going to be a permutation because order matters. So it's going to be 30 permuted, 1, 2, 3, 4 different ways, 4 different cabinets, 4 different offices. All right. Get on your calculator, dial that up. What is 30 permuted 4 ways? Oh, this might take a while. There's going to be 657,720 different cabinets you can arrange from 30 candidates, where one has to hold office of presidency, vice presidency, treasurer, and secretary. Okay. Is a permutation making sense, ladies and gentlemen? Making any sense here? All right. I want to end here today because I want to remain in sync with my face-to-face section. As I will write the remainder of my lecture notes to finish up this section, and then we'll wrap up the lecture portion of Math 130 by looking at 8.7. We'll look at some basic probability rules, okay? And so I will bid you adieu. You guys have a great weekend, and hopefully I'll see you on Monday to wrap up the lecture, last section, or the tail end of this section and the last section of the course. I'll hang on the line for a couple minutes if you have any questions. If not, have a great weekend. Stay safe.